Hello and welcome back. Before we begin, let me tell you something true about the hand resting on the blanket. It is almost entirely empty, not figuratively, measurably. Every atom in it consists of a nucleus with a cloud of electrons around it, and the nucleus is unimaginably small compared to the space that cloud occupies. If an atom was scaled up so that its nucleus were the size of a marble sitting in the middle of a football stadium, the electrons would be a faint haze somewhere out around the highest seats, and everything in between would be nothing at all. By volume, an atom is around 99.999999% empty space, which means your hand is that empty. So is the blanket, so is the bed and the floor and the planet under it. Solidity is not a property of matter. It's a property of the electrical forces between electron clouds, which refuse to overlap and so hold everything apart at a distance. Now here's the thought that leads to tonight's subject. Suppose you could remove all that empty space, press the electrons into the nuclei, and pack the remaining material together with nothing left between. Every person alive today, all 8 billion of us, all the bone and blood and water and breath, would fit comfortably inside a single sugar cube. That's not a wild estimate. It's a straightforward calculation, and the answer comes out roughly the size of something you'd stir into a cup of tea. And that is not a thought experiment. There are objects in this galaxy where exactly that has happened, where the empty space has been squeezed out of matter entirely by gravity, and what remains is packed at the density of an atomic nucleus, in a sphere about the width of a city. They're called neutron stars. A teaspoon of one would weigh about 1 billion tons, roughly the mass of every human being on Earth, in a spoon. Tonight, we're going to spend a couple of hours understanding how that's possible, slowly, with nothing for you to remember and nowhere to arrive. Let your shoulders come down, and we'll begin with the emptiness. Let's stay with the emptiness for a chapter, because everything tonight is about removing it. An atom has a nucleus of protons and neutrons at its center, and it's tiny, about 100,000th the width of the atom as a whole. All the mass is essentially there. Electrons contribute less than 1,000th of the total. So an atom is a very heavy speck, surrounded by an enormous, almost weightless region of nothing much. Why don't the electrons simply fall in? They're negatively charged, and the nucleus is positive, so they're attracted. In the earliest models, people imagined them orbiting like planets. But an orbiting charge should radiate energy and spiral inward within a fraction of a second, which plainly doesn't happen. The answer is quantum mechanics, and it's the most important idea for tonight. An electron isn't a small ball with a position. It's described by a wave, and confining a wave to a smaller region raises its energy sharply. So squeezing an electron closer to the nucleus costs energy, and there's a lowest energy arrangement below which it simply cannot go. That arrangement sets the size of the atom. It's not a shell or a container. It's the outcome of a balance between electrical attraction pulling inward and the quantum cost of confinement pushing outward. So the emptiness of matter is a quantum fact rather than a structural one. Nothing is holding the space open. The space is simply what it costs to have electrons at all. There's a second quantum rule, and it's the one that does the heavy lifting later tonight, so let's meet it gently. It's called the Pauli exclusion principle, formulated in 1925 by Wolfgang Pauli, and it says that no two electrons can occupy the same quantum state at the same time. Two electrons cannot be in the same place doing the same thing. That sounds like bookkeeping, and it has enormous consequences. It's why atoms have shells. Electrons fill up the available states from the bottom, and once a state is taken, the next electron must go into a higher one, which is why the periodic table has the shape it does, and why chemistry exists at all, and therefore why anything interesting has ever happened. But its most striking consequence is a kind of pressure. If you try to squeeze a collection of electrons into a smaller volume, they must occupy higher and higher energy states, because the low ones are already full and no two can share. That resistance is real, measurable, and enormous. And it has nothing to do with electrical repulsion or with heat. It's called degeneracy pressure, and it exists even at absolute zero, in matter with no thermal energy at all. Cool, a gas of electrons to nothing, and it still pushes back, purely because of a counting rule about which states are allowed. Remember that phrase, degeneracy pressure. It's what holds up a white dwarf, and when it fails, you get a neutron star, and when the neutron version fails, you get a black hole. The whole hierarchy of dead stars is a story about that one rule and where it gives way. Now let's go up in scale, to the objects that make neutron stars, and the principle is very simple. A star is a contest between two things. Gravity pulls its enormous mass inward, continuously trying to collapse it, and the pressure of hot gas, heated by nuclear fusion in the core, pushes outward. When those balance, the star sits stable, and it can sit that way for a very long time. Our Sun has been doing that for 4.5 billion years, and will continue for about 5 billion more. It fuses hydrogen into helium in its core, releasing energy, which maintains the temperature, which maintains the pressure, which holds up the weight of everything above. That's the entire life story of a star, fuel maintaining a balance. And it means the ending is inevitable, because fuel runs out. What happens then depends almost entirely on mass. A star like the Sun swells into a red giant, sheds its outer layers gently, and leaves behind a white dwarf, a hot core held up by exactly the electron degeneracy pressure we just discussed, cooling slowly for billions of years. A much more massive star has a different and far more dramatic ending, and it happens quickly. That's where neutron stars come from. So let's follow on. Take a star 10 or 20 times the mass of the Sun. It's brilliant, thousands or tens of thousands of times more luminous, and it burns through its fuel at a catastrophic rate. Where our Sun will last 10 billion years, such a star lasts perhaps 10 to 20 million. The extra mass means more gravity, which means a hotter core, which means fusion proceeds far faster. Massive stars live spectacularly and briefly. When the hydrogen in its core runs out, the core contracts and heats, and at higher temperature, helium begins to fuse into carbon and oxygen. That's the second stage, and it's shorter than the first. Then helium runs out, and the core contracts again, and carbon fuses into neon and magnesium. Then neon, then oxygen, then silicon. Each stage requires a higher temperature. Each releases less energy per reaction, and each is dramatically shorter than the one before. The numbers are striking. Hydrogen burning might take 10 million years, helium 1 million, carbon 1,000, neon a few years, oxygen a few months, and silicon burning, the last stage, takes about a day. So a star that has existed for 10 million years spends its final day fusing silicon into iron at a temperature of billions of degrees, with an onion-like structure of shells burning different elements at different depths, and a growing core of iron at the center that cannot burn at all. Iron deserves its own chapter, because it's the hinge on which the whole story turns. Fusion releases energy because the products are more tightly bound than the ingredients. When light nuclei combine, the resulting nucleus weighs slightly less than the parts, and the missing mass comes out as energy. But that only works up to a point. Binding energy per particle rises as you fuse light elements together, peaks around iron and nickel, and then falls again. Iron is the most tightly bound nucleus there is, which means fusing iron into anything heavier doesn't release energy, it consumes it. The one process that has held the star up for its entire life stops working permanently the moment the core becomes iron. So an iron core accumulates at the center, inert, growing as the shells above continue to burn silicon and dump more iron onto it. It's held up by electron degeneracy pressure, the same quantum rule that supports a white dwarf. And that support has a limit. Once the iron core exceeds roughly 1.4 solar masses, a threshold calculated by Subramanian Chandrasekhar in 1930, on a ship traveling from India to England when he was 19, the electrons cannot hold it any longer. At that moment, after 10 million years of stability, the core has about a quarter of a second left. What happens next is the most violent event in the modern universe, and almost all of it occurs faster than a blink. The core collapses. In under a second, a region roughly the size of the Earth falls inward to a sphere about 20 kilometers across. The infall speeds reach a substantial fraction of the speed of light, around a quarter of it, by the time the material arrives at the center. As the density rises, something remarkable happens to the matter itself. The electrons are squeezed so hard that it becomes energetically favorable for them to merge with protons, converting each pair into a neutron and releasing a neutrino. That process is called neutronization, and it has two effects. It removes the electrons whose degeneracy pressure was providing support, accelerating the collapse, and it produces an enormous flood of neutrinos, which stream outward carrying away energy. The collapse continues until the material reaches the density of an atomic nucleus, at which point the neutrons themselves begin to resist, both by their own degeneracy pressure and by the strong nuclear force, which becomes strongly repulsive at very short range. At that point, the collapse halts abruptly, and the infalling core, arriving at speed, bounces. A shockwave forms and begins to travel outward through the star. That shockwave initially stalls, and for decades, this was the great unsolved problem in the theory. The bounce alone doesn't seem to produce an explosion. The shock loses energy breaking apart the nuclei it passes through and grinds to a halt. What appears to revive it is the neutrinos. The newly formed neutron star at the center is extraordinarily hot, hundreds of billions of degrees, and it radiates almost its entire gravitational binding energy as neutrinos over the following 10 seconds or so. Neutrinos barely interact with anything, but there is so much material at such high density just above the core that a small fraction of them, perhaps 1%, is absorbed, and that fraction deposits enough energy to reheat the stalled shock and drive it outward. 1% of the neutrino energy is enough to blow apart the entire outer star, which tells you how enormous the total is. About 99% of the energy of a core collapse supernova leaves as neutrinos invisibly. The light we see, bright enough to briefly outshine an entire galaxy, is a fraction of a percent of the total. The shock then takes hours to reach the surface, and when it does, the star brightens dramatically. For weeks it shines with the light of billions of suns, and then fades over months, leaving an expanding cloud of debris seeded with newly forged elements. And at the center, exposed, is the object that stopped the collapse, a neutron star, a few tens of kilometers across, containing more mass than the Sun, spinning rapidly, extraordinarily hot, and about to cool for the next several billion years. There's one occasion when all of this was directly confirmed, and it happened within living memory. On the 23rd of February 1987, 3 separate detectors, in Japan, in the United States, and in Russia, each recorded a brief burst of neutrinos. In total, about 24 events, spread over roughly 13 seconds. A few hours later, astronomers in the southern hemisphere noticed a new bright star in the Large Magellanic Cloud, a satellite galaxy about 160,000 light-years away. It was the brightest supernova observed since the invention of the telescope, and it was visible to the naked eye for months. The neutrinos had arrived first, which is exactly what the theory predicted. They escape the collapsing core immediately, while the light has to wait hours for the shockwave to reach the surface and break out. 24 detected particles, from an event that produced something like 10 to the 58th of them. And that handful confirmed the entire picture: the collapse, the neutronization, the duration of the cooling, the energy budget. The timing and the numbers matched what had been calculated. It's still the only supernova from which neutrinos have been detected, and it's regarded as one of the most important observations in astrophysics. It's also a good example of how thin the evidence sometimes is. An entire theoretical framework, confirmed by 20-odd particles arriving over 13 seconds, one evening in 1987. The neutron star that should have formed at the center was not seen for decades, and its absence puzzled people. Recent observations have found evidence for a compact object hidden inside the dust, which is a satisfying resolution to a 30-year wait. Let's lay out what's left behind, slowly, because the numbers are the whole point. A typical neutron star has a mass of about 1.4 times the Sun, though the range extends from around 1.2 up to a bit over 2. That's more material than our entire star, which is 1,000,000 times the volume of the Earth. Its diameter is about 20 kilometers. You could drive across it in 15 minutes if there were anything like a road, which there is not. It's the size of a city. So the density comes out at around 10 to the 17th kilograms per cubic meter, roughly the density of an atomic nucleus, because that's essentially what it is, a single enormous nucleus, held together by gravity rather than by the strong force alone. A teaspoon of that material, 5 cubic centimeters, would have a mass of about 500 million to 1 billion tons, comparable to a mountain or to the total mass of every human being alive in a spoon. The surface gravity is around 200 billion times Earth's. An object dropped from 1 meter above the surface would strike it at something like 2,000 kilometers per second in a few microseconds. And it spins, newly formed, typically many times per second, because the collapsing core conserved its angular momentum while shrinking by a factor of 100,000. The same effect that makes a skater speed up when they pull their arms in, taken to an extreme. Let's actually do the teaspoon calculation, gently, because it's satisfying to see where the number comes from. Start with the nucleus of an atom. Its density is about 2 times 10 to the 17th kilograms per cubic meter, a number known from nuclear physics, measured in laboratories, entirely independent of astronomy. A teaspoon is 5 milliliters, which is 5 times 10 to the minus 6 cubic meters. Multiply, and you get about 1 billion kilograms, 1,000,000 tons. That gives 1,000,000 tons per teaspoon at nuclear density, and you'll often hear 1 billion. The difference comes down to which figure people use for the interior. The core of a neutron star is denser than an ordinary nucleus, perhaps 5 to 10 times denser, and different sources use different volumes for a teaspoon and different points in the star. So the honest range is roughly 100 million to a few billion tons per teaspoon, depending on where in the star you scoop and how generous your spoon is. I mention that not to be pedantic, but because it's a nice illustration of how these popular numbers work. They're order of magnitude statements, and the underlying physics is solid, and the exact figure varies with the assumptions. The comparison that always lands for me is this one. A cubic centimetre of neutron star material, a sugar cube, weighs about as much as a large mountain, and the whole object, containing more mass than the Sun, is the size of a modest city. Which is a way of saying that nearly all the volume of ordinary matter really is empty, and that gravity, given enough mass, is entirely capable of taking it away. Here's a way to feel the gravity, and it's a calm thought experiment despite the numbers. Drop something from 1 meter above a neutron star's surface. On Earth, that takes about half a second, and it lands gently. There, the acceleration is around 200 billion times stronger. The object would cross that meter in a few millionths of a second, arriving at roughly 2,000 kilometers per second, about 1% of the speed of light. The energy released on impact, per kilogram, would exceed a substantial nuclear explosion. Which is why matter falling onto a neutron star produces such spectacular displays. When a neutron star has a companion star and pulls gas off it, that gas arrives with enormous energy, heats to millions of degrees, and radiates in X-rays. The efficiency is remarkable. Dropping material onto a neutron star converts something like 10 to 20% of its rest mass into energy, compared to less than 1% for nuclear fusion. Gravity, in that regime, is a far better energy source than fusion. The escape velocity from the surface is around half the speed of light, so light leaving the surface is significantly redshifted, and light passing nearby is bent so strongly that you can see somewhat around to the far side. More than half of the surface is visible at once, which is not true of any ordinary object. There's nothing to stand on, of course. Nothing made of atoms could exist there. Any object would be flattened into a film of material 1 atom thick and then absorbed. But the geometry is real, and the light bending has been measured. Let's return to the physics that stops the collapse, because it's the reason these objects can exist at all. Once the electrons have merged with protons, what remains is neutrons, an enormous number of them, packed at nuclear density. And neutrons obey the same exclusion rule that electrons do. No two can occupy the same quantum state. So the same degeneracy pressure appears, but now from neutrons. And because neutrons are nearly 2,000 times heavier than electrons, the pressure they generate at a given density is far greater. That's why a neutron star can support more mass in a much smaller volume than a white dwarf can. But degeneracy pressure alone isn't the whole story, and this is a detail often left out. At these densities, the strong nuclear force also contributes substantially. The same force that binds nuclei together becomes strongly repulsive when nucleons are pushed too close, and that repulsion provides a large fraction of the support. Which is why the maximum mass of a neutron star is genuinely uncertain. The electron case can be calculated cleanly, because electrons barely interact, and the physics is simple. The neutron case depends on how the strong force behaves at densities beyond anything reproducible in a laboratory, and nobody can calculate that from first principles. So we have an object whose existence depends on a quantum counting rule, whose exact properties depend on nuclear physics we can't compute, and whose interior is the least understood ordinary matter in the universe, which makes it, for physicists, one of the most interesting places to look. Neutron stars have layers, and the structure is genuinely strange. So let's take a slow tour from the outside inward. It's a peaceful thing to think through. At the very top, there's an atmosphere, a layer of plasma, mostly hydrogen or helium, perhaps a few centimeters thick, not kilometers, centimeters. The gravity is so overwhelming that the atmosphere is compressed into something thinner than a book. The temperature there can be 1,000,000 degrees, and it's what produces most of the X-rays we see from cooling neutron stars. Modeling that atmosphere is essential for interpreting the observations, and it's difficult because the magnetic fields are so strong that atoms are distorted into elongated shapes, with their electron clouds squeezed into cigars along the field lines. Below the atmosphere is an ocean, in some models, a layer of liquid, perhaps a meter or so deep, of extremely hot and dense material. And then the surface proper, a crust, crystalline, made of nuclei, arranged in a lattice with free electrons flowing between them. Structurally, it's like a metal, though far denser than anything on Earth. That crust is thought to be the strongest material in the universe. Simulations suggest it's around 10 billion times stronger than steel. Its resistance to being broken exceeds anything we can make by a factor that has no useful comparison. It's also extremely smooth. The gravity is so strong that any bump is flattened. Calculations suggest the tallest features on a neutron star's surface are perhaps a fraction of a millimeter high. A mountain on such a star would be invisible to the naked eye. Deeper in the crust, something happens that I find genuinely delightful, and it has the best terminology in physics. As you descend, the pressure rises, and the nuclei are squeezed closer together. Ordinarily, they repel each other electrically, keeping a spherical shape, but at extreme density, the competition between that repulsion and the attractive strong force produces something unexpected. The nuclei stop being spheres and start merging into extended shapes. First they form long cylinders, packed side by side. Then those cylinders merge into sheets, stacked in layers. Then the arrangement inverts, and you get sheets of empty space in a sea of nuclear matter, then tubes of emptiness, then bubbles. Physicists, being human, name these phases after pasta. The cylinders are spaghetti, the sheets are lasagna, the tubes are bucatini or spaghetti with holes. The bubbles, in some naming schemes, are Swiss cheese or anti-gnocchi. This is a real field of research, with real papers and real simulations, and the terminology is entirely standard. Nuclear pasta is the accepted name for the deepest layer of a neutron star's crust. And it matters, because those structures determine the crust's strength, its electrical and thermal conductivity, and how it responds to stress, all of which affect the observations. The lasagna phase in particular seems to be extremely resistant to shearing, which contributes to that enormous strength figure. So somewhere down there, a few hundred meters below the surface, Matter arranges itself into sheets and tubes at the density of a nucleus, for reasons of pure force balance, and someone had to name it, and they chose pasta. I think that's a wonderful thing to know at this hour. Below the crust is the outer core, and it's stranger still. Here, the nuclei have dissolved entirely. What remains is a fluid of neutrons, with a small fraction of protons and electrons mixed in, perhaps 5%, and it's not an ordinary fluid at all. At these densities and temperatures, the neutrons are thought to become a superfluid. That's a state of matter observed on Earth in helium-cooled too, within a couple of degrees of absolute zero, and its defining property is zero viscosity. It flows with absolutely no friction. Superfluid helium does remarkable things in the laboratory. It creeps up the walls of its container and over the rim. It flows through openings too small for any ordinary liquid. Set it rotating and it will continue indefinitely, because there's nothing to slow it. The protons, meanwhile, are thought to become a superconductor, carrying electrical current with no resistance whatsoever, which has profound implications for how the star's magnetic field is arranged and maintained. Which means the interior of a neutron star may be a frictionless sea of neutrons, threaded with resistanceless currents of protons, at a temperature of hundreds of millions of degrees. That seems backwards. Superfluids on Earth require extreme cold. But what matters is temperature relative to the energy scale of the system. And for nuclear matter, that scale is so high that hundreds of millions of degrees counts as very cold indeed. It's freezing by the standards of a nucleus. There's observational evidence for that superfluid interior, and it comes from a peculiar behavior that pulsars occasionally show. A neutron star's rotation slows gradually and extremely predictably as it radiates energy. The spin down is so regular that the timing can be modeled to extraordinary precision over years. But occasionally, irregularly without warning, a pulsar suddenly speeds up. A tiny amount, typically a fraction of a millionth of its rotation rate, over a period of less than a minute. Then it resumes its gradual slowdown, sometimes with a slightly altered pattern. These events are called glitches, and hundreds have been recorded. The Vela pulsar produces one every couple of years, reliably enough that observers watch for them. The leading explanation involves the superfluid. In a rotating superfluid, the rotation isn't smooth. It's carried by discrete vortices, quantized whirlpools, and their number determines the rotation rate. Those vortices can become pinned to the crust's crystal lattice. So as the crust slows, the superfluid keeps rotating faster, held back by pinning, and the difference builds. Eventually, a large number of vortices unpin at once, transferring angular momentum abruptly to the crust, and the whole star speeds up in an instant. Which means every glitch is direct evidence of a frictionless quantum fluid, tens of kilometers beneath the surface of an object thousands of light years away, detected by watching a radio signal tick. And then there's the inner core, and here the honest answer is that nobody knows. At the center, the density exceeds that of an atomic nucleus by a factor of perhaps 5 to 10. No laboratory can produce those conditions, and the theory of the strong force cannot be solved directly in that regime. The calculations become intractable in a way that has resisted decades of effort. So there are competing possibilities, and choosing between them is one of the field's central problems. The conservative option is that it's simply more of the same. Neutrons, protons, and electrons at higher density, with the interactions becoming more complicated, but the constituents unchanged. Another possibility is that new particles appear, hyperons, which are heavier cousins of neutrons containing strange quarks. At sufficient density, it might become energetically favorable to convert some neutrons into these heavier particles, which would soften the pressure and lower the maximum possible mass. And the most dramatic option is that the neutrons dissolve entirely. Protons and neutrons are made of quarks, normally confined inside them by the strong force. At extreme density, the boundaries might break down, producing a sea of free quarks, quark matter, with no individual nucleons at all. If that happens, the center of a neutron star would be a phase of matter that exists nowhere else in the present universe, and which last existed everywhere in the first microseconds after the beginning. That uncertainty has a name, the equation of state, and it's worth a chapter, because it's the thing most neutron star research is ultimately trying to determine. An equation of state is simply the relationship between pressure and density for a material. For an ordinary gas, it's straightforward and was worked out centuries ago. For nuclear matter at extreme density, it's unknown. And it matters because it determines everything measurable about a neutron star. A stiffer equation of state, one where pressure rises steeply with density, produces larger, less compressible stars that can support more mass. A softer one produces smaller stars with a lower maximum mass. So if you can measure the masses and radii of enough neutron stars precisely, you can work backwards and constrain what the matter inside must be doing, including whether hyperons appear or whether the quarks come unbound. That's the game. It's nuclear physics done by astronomy, because the relevant conditions exist only inside these objects and nowhere we can build. And there's been real progress. Measurements of unusually massive neutron stars over 2 solar masses rule out the softest equations of state, because those couldn't support that much. Radius measurements from X-ray observations narrow it further. Gravitational waves from a merger provided another constraint entirely, by revealing how much the stars deformed each other before colliding. Slowly, from several completely different directions, the space of possibilities is closing. It's one of the more satisfying convergences in modern physics, and it isn't finished. We've covered density. Now let's cover the other extreme property, which is just as remarkable. Neutron stars have magnetic fields of about 1 trillion times the Earth's, typically 10 to the 8th or 10 to the 12th times stronger than anything we can produce in a laboratory, even briefly. The reason is the same as the spin: conservation. A star has a magnetic field threading through it, and when the core collapses from the size of the Earth to 20 kilometers, the field lines are compressed along with the material. Squeeze the area by a factor of 100,000 squared, and the field strength rises by the same factor. Fields that strong do peculiar things to matter. They distort atoms into elongated shapes, squeezing the electron clouds into narrow cylinders along the field direction. They change the properties of the vacuum itself, making empty space birefringent, able to split light into 2 components traveling at different speeds, an effect predicted in the 1930s and reported observationally around a neutron star in 2016. And they channel everything. Charged particles cannot cross field lines easily, so any material approaching a neutron star is funneled along the field toward the magnetic poles, arriving in concentrated hotspots rather than spread over the surface. That funneling, combined with rapid rotation, produces the phenomenon that made neutron stars famous, and which was discovered by accident by a graduate student in a field in Cambridge. In 1967, Jocelyn Bell was a doctoral student who had spent 2 years helping to build a radio telescope out of wooden posts and wire, spread across 4 acres by hand. The instrument produced its data as ink on paper, about 30 meters of chart recording per day, which she analyzed personally. Over months, she became familiar with every kind of interference: passing cars, thermostats, radar. And then she noticed something that didn't fit. A small amount of what she called scruff, appearing at the same position in the sky night after night. It was faint, and it occupied about 1 centimetre of 100 meters of chart. She persuaded her supervisor to record that patch at higher speed, which took weeks of trying, and eventually the signal resolved into a series of pulses, perfectly regular, one every 1.33 seconds. Nothing natural was known to produce such precise repetition. The regularity was so machine-like that the possibility of an artificial origin was seriously discussed, and the source was labelled, half in jest, LGM1, for little green men. Then Bell found a second source, in a different part of the sky, with a different period. 2 independent civilizations, both signaling Earth on the same frequency, seemed unlikely, and the natural explanation began to look plausible instead. The discovery paper appeared in early 1968, and within months, the objects had been identified as rapidly rotating neutron stars. objects that had been predicted in the 1930s and never observed. The Nobel Prize for the discovery went to her supervisor and a colleague in 1974, and not to her, which caused considerable controversy that continues to be discussed. She has spoken about it with remarkable grace over the decades, and in 2018 she was awarded a large prize of her own, which she donated in its entirety to fund physics scholarships for students from underrepresented groups. The mechanism is elegant, and once you see it, the regularity makes sense. A neutron star has a magnetic field, and, crucially, the magnetic axis is usually tilted relative to the rotation axis, just as Earth's magnetic poles don't coincide with its geographic ones. Charged particles are accelerated along the field lines near the magnetic poles to enormous energies, and they radiate. The radiation is beamed, concentrated into narrow cones emerging from the two magnetic poles. Now spin the whole thing. The beams sweep around like the beam of a lighthouse, and if the geometry happens to be right, if one of those beams sweeps across the Earth, we receive a pulse once per rotation. That's the whole model, proposed within a couple of years of the discovery, and it explains everything. The precision, the stability, the fact that only some neutron stars appear as pulsars. Most have beams that never point our way. The pulses can be extremely fast. The one Bell found took 1.3 seconds, others take mere milliseconds, and the regularity is astonishing. Some pulsars keep time to a precision comparable to the best atomic clocks over years. Which means that scattered through the galaxy are thousands of natural clocks, each ticking with extraordinary precision, each visible across enormous distances. And that has turned out to be one of the most useful facts in astronomy. Let's dwell on that precision, because it's what makes pulsars scientifically valuable rather than merely picturesque. A millisecond pulsar can have its pulse arrival times predicted years in advance to within a fraction of a microsecond. That's a stability comparable to the atomic clocks that define our unit of time, produced by an object 20 kilometers across, thousands of light years away, spinning hundreds of times per second. The stability comes from the enormous rotational inertia. A neutron star carries a colossal amount of angular momentum in a very compact package, so nothing much can disturb it. It slows very gradually as it radiates energy, and that slowdown is itself so regular that it can be modeled and subtracted. Which means any unmodeled deviation in the arrival times is information. Something must have interfered, either along the path or at the source or at our end. That's the basis of pulsar timing as a technique, and it has been used for a remarkable range of purposes. Measuring the interstellar medium the signals pass through, testing general relativity in strong fields, detecting planets, and most recently detecting gravitational waves of enormously long wavelength. The slowdown also gives an age. If you know how fast it's spinning and how fast that's changing, you can estimate how long it's been going, the characteristic age. For the Crab pulsar, that calculation gives around 1,000 years, and we know independently that the supernova was seen in 1054, which is a rather satisfying check. Most pulsars slow down over millions of years and eventually fade. Once the rotation drops below a certain rate, the mechanism that produces the beams stops working and the object goes quiet. But some don't. There's a population of pulsars spinning hundreds of times per second, and their ages, by other measures, are enormous, billions of years. Something has spun them back up. The explanation is called recycling. If a neutron star has a companion star, and that companion swells in old age, material can flow across onto the neutron star. That material carries angular momentum, and as it spirals in through a disk and lands, it spins the star up, over millions of years, back to millisecond periods. So a millisecond pulsar is an old, cooled neutron star that has been given a second life by a companion. There's direct evidence for the process. Systems have been observed switching between accreting X-ray sources and radio pulsars over months as the material flow varies. The fastest known spins about 716 times per second. Its surface at the equator is moving at roughly a quarter of the speed of light. Think about that for a moment. An object with more mass than the Sun, 20 kilometers across, completing 700 rotations every second, faster than a kitchen blender, with its equator moving at 75,000 kilometers per second, held together against that by gravity alone. And it's been doing that steadily for longer than the Earth has existed. There's a subclass with magnetic fields even more extreme, and they're the most violent objects in the galaxy short of a black hole. Magnetars have fields of 1,000 times a typical pulsar's, around 10 to the 15th times the Earth's. They're thought to form when the collapsing core is spinning fast enough that a dynamo process amplifies the field enormously during the first seconds. At those field strengths, the magnetic energy itself becomes structurally significant. The field stresses the crust from beneath, building strain until something gives. And when the crust cracks and shifts, the field lines reconnect and release energy suddenly. The largest such event ever observed came from a magnetar about 28,000 light-years away in December 2004. For a fifth of a second, it emitted more energy than our Sun produces in 250,000 years. And it affected the Earth. From 28,000 light-years away, the burst of gamma rays ionized the upper atmosphere, measurably disturbing the ionosphere and affecting radio propagation. Several spacecraft detectors were saturated, overwhelmed, unable to record the peak. Calculations suggested that if such an event happened within about 10 light-years, it could do real damage to the atmosphere. The nearest known magnetar is thousands of light-years away, and the population is small, perhaps a few dozen known, so there's no scenario in which this matters to anyone here. But it's a striking illustration of what a magnetic field can do when it's strong enough to break the strongest material in the universe. That cracking has a name, and it's worth a chapter. The crust of a neutron star is rigid, extraordinarily so, as we said, perhaps 10 billion times stronger than steel. But it's under stress from two directions. As the star spins down, its shape changes. A rapidly rotating body bulges at the equator. As rotation slows, the equilibrium shape becomes more spherical. But a rigid crust can't flow smoothly into a new shape. It holds and strain accumulates until it fractures. And in magnetars, the magnetic field adds enormous additional stress from below. When the crust fails, the readjustment is tiny, perhaps a micrometer. But the energy released is colossal, because everything about these objects is colossal. The event is called a starquake, and it can produce a burst of X-rays or gamma rays, and can also cause a glitch in the rotation. Some observations of magnetars have revealed oscillations in the aftermath of a giant flare, the whole star ringing at frequencies determined by its structure, like a struck bell. That field is called astroseismology, and in principle, those oscillations carry information about the interior, which is otherwise inaccessible. So a crack, a micrometer wide, in a crust a kilometer thick, on an object 20 kilometers across, tens of thousands of light-years away, produces a signal we can detect and use to probe the densest matter in existence. There's something quite satisfying about that chain. Let's spend a chapter on the most famous neutron star, because its story spans 1,000 years. In July 1054, astronomers in China recorded a guest star appearing in the constellation we call Taurus. It was bright enough to be visible in daylight for over 3 weeks, and remained visible at night for nearly 2 years before fading. Records of the same event appear in Japanese and Arabic sources, and possibly in rock art in what is now the southwestern United States, though that identification is debated. What they saw was a supernova, about 6,500 light-years away, and what it left behind is the Crab Nebula, an expanding cloud of glowing filaments, one of the most photographed objects in the sky, still visibly growing at over 1,000 kilometers per second. At its center is a neutron star, spinning about 30 times per second, and it was one of the first pulsars identified after Bell's discovery. The connection was decisive. It tied pulsars firmly to supernova remnants and confirmed that these objects are the collapsed cores of exploded stars. The Crab pulsar is also unusually energetic. It pumps enough energy into the surrounding nebula to make it glow across the entire electromagnetic spectrum, and the nebula would have faded long ago without that continuous supply. So there's an object above us, visible in a modest telescope, whose formation was written down by astronomers 970 years ago, and whose central engine is still running, a 20-kilometer sphere turning 30 times a second, illuminating a cloud 6 light-years across, having been doing so continuously since before the Norman conquest of England. Here's a piece of history that surprises people. The first planets discovered outside our solar system were not orbiting a normal star. They were orbiting a pulsar. In 1992, an astronomer named Alexander Wolfson, working with Dale Frail, announced the detection of 2 planets around a millisecond pulsar about 2,000 light-years away. A third was found later. The technique used exactly the precision we discussed earlier. If a pulsar has planets, their gravity makes it wobble slightly, which changes the distance to us periodically, which shifts the arrival times of the pulses by tiny amounts in a repeating pattern. The precision was such that they could detect planets smaller than the Earth, better sensitivity than any technique used for ordinary stars even today. One of the objects is around twice the mass of our Moon, which remains among the smallest exoplanets known. That was 3 years before the first planet was found around a Sun-like star, and it was met with considerable caution, partly because a previous pulsar planet claim had been retracted after turning out to be an error in accounting for the Earth's own motion. Nobody knows how those planets got there. A supernova should destroy or eject any pre-existing planetary system. The leading idea is that they formed afterwards, from a disk of debris, perhaps the remains of a companion star that was disrupted. Which gives an image worth sitting with: worlds circling a dead star, formed from the wreckage of another star, bathed in radiation, in a system where the Sun is 20 kilometers across and flashes hundreds of times per second. Some of the strongest tests of general relativity have come from pulsars in binary systems, and the story is a good one. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar orbiting another neutron star. The timing precision meant they could measure the orbit in extraordinary detail and watch it change. General relativity predicts that 2 massive objects in a tight orbit should radiate gravitational waves, losing energy, so the orbit slowly shrinks and the period shortens. The predicted rate for that system was tiny, about 75 microseconds per year. They measured it. Over years of observation, the orbital period decreased at exactly the predicted rate, matching the theory to within a fraction of a percent. That was the first evidence, indirect but compelling, that gravitational waves exist, 4 decades before they were detected directly. It won the 1993 Nobel Prize. Then, in 2003, something better was found. A system where both neutron stars are visible as pulsars, the double pulsar. 2 clocks orbiting each other every 2.5 hours, allowing measurements of unprecedented precision. That system has tested general relativity to better than 1 part in 10,000, confirmed several relativistic effects at once, and continues to improve as observations accumulate. It's among the most stringent tests of the theory anywhere. And the orbit is shrinking measurably on schedule. The 2 will merge in about 85 million years, in an event that would be detectable across a substantial fraction of the universe. On the 17th of August 2017, that kind of merger was observed directly, and it became one of the most productive single events in the history of astronomy. Gravitational wave detectors in the United States and Italy registered a signal lasting about 100 seconds, much longer than the black hole mergers they'd seen before, and rising to higher frequencies, which is the signature of lighter objects spiraling together. 2 neutron stars, about 130 million light-years away. Less than 2 seconds later, a gamma-ray burst was detected from the same direction by orbiting telescopes. And then an alert went out, and within about 11 hours, optical telescopes had located the source in a galaxy in the constellation Hydra. Over the following weeks, around 70 observatories on every continent and in orbit observed it across the entire electromagnetic spectrum. Thousands of astronomers were involved. It was the first time an event had been observed in both gravitational waves and light, the beginning of what people call multi-messenger astronomy. And the light told an extraordinary story. The glow that followed the merger, called a kilonova, brightened and reddened over days in a very particular way, exactly as predicted for the radioactive decay of freshly created heavy elements. Which brings us to where gold comes from, and it's the best answer this subject has to offer. Most elements are made in stars, by fusion, hydrogen into helium, helium into carbon and oxygen, and so on up to iron. But fusion stops at iron, because beyond it, fusing costs energy rather than releasing it. So everything heavier than iron, silver, gold, platinum, lead, uranium, has to be made some other way. And the way involves neutrons. If a nucleus is bathed in free neutrons, it can absorb them. Neutrons have no charge, so there's no electrical repulsion to overcome. They simply stick. And an overloaded nucleus will eventually convert one of those neutrons into a proton, moving it up the periodic table. There are two versions. The slow process happens inside certain aging stars over thousands of years, with neutrons arriving occasionally, and it produces about half the heavy elements. The rapid process requires an enormous flood of neutrons in a fraction of a second, so many that nuclei absorb dozens before having time to decay. And it produces the rest, including most of the gold and all of the uranium. For decades, nobody was sure where the rapid process happened. Supernovae were the leading candidate, but the calculations kept struggling to produce enough neutrons. Neutron star mergers were the other possibility, and in 2017, the evidence arrived. The kilonova's brightness, color, and evolution matched predictions for freshly synthesized heavy elements decaying radioactively, and the estimated yield from that single event was several Earth masses of gold, and considerably more of other heavy elements. Let's sit with that for a moment, because it connects tonight's subject to something ordinary. If there's any gold in the room, a ring, a chain, the plating on a connector, those atoms were made in an event like the one observed in 2017, or possibly in a rare kind of supernova billions of years ago, before the sun existed. The material was flung outward at a substantial fraction of the speed of light, drifted through interstellar space, mixed into a molecular cloud, and eventually was gathered up into the disk that formed our solar system 4.5 billion years ago. Some of it settled into the Earth. Most of that sank into the core during the planet's molten youth. What's accessible near the surface probably arrived later, in a bombardment of asteroids. And then it sat in rock for billions of years until someone dug it up. So a gold ring has a specific and rather extraordinary history, forged in the collision of two dead stars, thrown across the galaxy, incorporated into a planet, buried, mined, and worn. The same is true of the platinum in a catalytic converter, and the uranium in a reactor, and the iodine in your thyroid, which is a heavy element too, and follows the same route. There aren't many facts that connect the extreme physics of collapsed stars to something you could hold in your hand. This is one, and it's exact rather than poetic. Let's walk through the merger itself, slowly, because the sequence is remarkable. Two neutron stars orbit each other, radiating gravitational waves, losing energy over millions or billions of years. The orbit shrinks imperceptibly at first, then faster, because the closer they get, the more strongly they radiate. In the final minutes, the orbit tightens rapidly. In the final seconds, they're circling hundreds of times per second, at a substantial fraction of the speed of light, and each is being visibly distorted by the other's gravity, stretched into an egg shape by tidal forces. How much they deform depends on the equation of state. A stiffer interior resists more, and that deformation affects the gravitational wave signal in a measurable way, which is how the 2017 event constrained the physics of the interior. The waves carried information about the stiffness of matter at nuclear density across 130 million light-years. Then they touch. The surfaces meet at enormous speed, and material is flung outward, a fraction of a solar mass of neutron-rich matter, ejected in tidal tails and in a hot wind driven off the merged remnant. That ejected material is the R process factory. Freed from the enormous pressure, the neutron-rich matter decompresses, nuclei form and capture neutrons rapidly, and within a second, the heavy elements are made. Then they decay radioactively, which heats the expanding cloud, which produces the kilonova glow that telescopes tracked for weeks. And the merged object at the center either collapses immediately into a black hole, or survives briefly as a hypermassive rotating neutron star before collapsing. Which of those happened in 2017 is still debated, and it matters, because the answer constrains the maximum mass. That maximum mass is one of the key numbers in the field, and finding it is a major goal. The principle is the same as for white dwarfs. Degeneracy pressure and the strong force can support only so much weight, and above some limit, nothing can prevent complete collapse. For white dwarfs, that limit is precise, about 1.4 solar masses, calculable from first principles. For neutron stars, it depends on the unknown equation of state, and the theoretical range spans roughly 2 to 2.5 solar masses, with some models allowing a little more. Observations have been narrowing it from below. Several neutron stars have been measured at 2 solar masses or slightly above, which immediately eliminated every model that couldn't support that much. The heaviest confirmed ones sit around 2.1 to 2.3, with some uncertainty. And the 2017 merger gave constraints from the other side. The combined mass was around 2.7 solar masses. An analysis of what happened afterwards, how quickly it collapsed, what the light curve showed, suggests the maximum is probably below about 2.3. So the answer is being squeezed from 2 directions. Measurements of heavy individual stars pushing the limit up, and merger analyses pushing it down. They're converging on something like 2.2 to 2.3 solar masses. Above that, there is nothing left. No known force can hold the material, and the collapse continues past the point where a horizon forms. There's a related puzzle worth a chapter, because it's been a live question for 30 years, and recent observations have complicated it. If neutron stars top out around 2.3 solar masses, and the lightest black holes formed from stellar collapse are around 5, then there should be very few objects in between. Astronomers observing X-ray binaries noticed exactly that. A scarcity of compact objects between about 2 and 5 solar masses. It was called the mass gap. Various explanations were proposed, mostly involving the details of how supernova explosions succeed or fail. Perhaps the physics naturally produces either a light remnant or a heavy one, with little in between. Then gravitational wave detectors began finding mergers, and objects started turning up in the gap. One event involved a compact object of about 2.5 solar masses, merging with a black hole. And nobody can say with confidence whether that object was the heaviest neutron star ever found or the lightest black hole. More such objects have since appeared, and radio observations have found at least one candidate in that range as well. So the gap may not be a gap at all. It may have been a selection effect in the older method, which relied on X-ray binaries and could only find objects in particular configurations. That's an example of how a new observational technique reshapes a field. 30 years of a well-established pattern, based on solid observations, turning out to be an artifact of what those observations were able to see. Measuring the radius is harder than measuring the mass, and the technique that finally worked is elegant enough to deserve a chapter. A NASA instrument mounted on the International Space Station since 2017, a set of X-ray detectors with very precise timing, was designed for exactly this. The method uses the hot spots. A pulsar's surface isn't uniform. Where the magnetic field channels particles onto the poles, there are patches hotter than the rest, and those patches rotate in and out of view, producing a varying X-ray signal. Now, the shape of that variation depends on gravity. Light from the far side is bent around toward us, significantly because the gravity is so strong, so the hotspot doesn't simply disappear when it rotates away. How much the signal dips and how the pulse profile is shaped depends on how strongly the light is bent, which depends on the ratio of mass to radius. So by modeling the pulse shape in detail, you can extract the radius. The calculations are demanding, and the analysis for a single star took years and enormous computing time. The results give radii around 11 to 13 kilometers for stars of about 1.4 solar masses, consistent with a moderately stiff equation of state and consistent across several stars measured. And there was a surprise. The hotspots weren't where the simple model predicted, two neat circles at opposite poles. The best-fitting maps showed spots in unexpected places and shapes, suggesting the magnetic field is considerably more complicated than a simple bar magnet, which is now its own research problem. Let's put them in context, because they're more common than most people assume. Our galaxy is thought to contain around 100 million to a billion neutron stars, the accumulated remnants of every massive star that has died in the last 12 billion years or so. We've detected roughly 3,000 as pulsars, plus a few hundred more in other ways. So we've found perhaps 1 in 100,000 of them. The reason is that most are invisible. A pulsar is only detectable if its beam happens to sweep across us, which requires a fortunate alignment. And pulsars fade. After 10 or 20 million years, the rotation has slowed enough that the emission mechanism shuts down and the star goes dark. So the galaxy is full of cold, dark, silent neutron stars, drifting between the stars, undetectable unless something happens to them. They're the invisible majority. There are also some that are isolated and still warm enough to emit X-rays from their surfaces as they cool. A small group, sometimes called the Magnificent Seven, found in X-ray surveys close by and quiet. The nearest known one is around 400 light-years away, an isolated, cooling neutron star with no companion, no pulsations of the usual kind, moving through space at over 100 kilometers per second. It's one of the few whose surface we can study directly, without the complications of accretion or beaming. A newborn neutron star is at hundreds of billions of degrees. Within a few years, it's down to 1 billion. After 1 million years, it might be a few 100,000 degrees at the surface, and it keeps falling. The cooling happens in 2 stages. For the first 100,000 years or so, the dominant mechanism is neutrino emission from the interior. Neutrinos are produced by various reactions in the dense core, and because they barely interact, they escape directly from the center, carrying energy straight out. That's remarkably efficient. It means the interior cools from the inside, rather than having to conduct heat to the surface first. Later, once the interior has cooled sufficiently, photon emission from the surface takes over, and the process slows considerably. The details depend on the composition of the core, which makes cooling curves another window onto the equation of state. If certain fast neutrino reactions are possible, which requires a particular proton fraction, the star cools much more quickly. So measuring the temperature of neutron stars of known ages constrains what's inside them. There's one case where cooling has apparently been observed in real time. The neutron star in a supernova remnant about 11,000 light-years away, which some analyses suggest has cooled measurably over a couple of decades of observation. The interpretation has been debated, and it may reflect instrumental effects, but if real, it will be direct evidence for superfluidity appearing in the core as the star crossed a critical temperature. Here's a curious fact. Neutron stars are typically traveling much faster than the stars they came from. Ordinary stars in the galactic disk move at perhaps 20 or 30 kilometers per second relative to their neighbors. Neutron stars average several hundred, and some exceed 1,000, fast enough to escape the galaxy entirely. Something kicks them during formation, and the leading explanation is that the supernova explosion is not symmetric. If the collapse and the subsequent explosion were perfectly spherical, the momentum would balance and the remnant would stay put. But simulations show the process is turbulent and lopsided. The neutrino emission and the ejected material are asymmetric, and even a small imbalance imparts a substantial recoil to an object of that mass. A few percent asymmetry in the ejector is enough to produce the observed speeds, and the neutrinos themselves may contribute. Because they carry so much of the total energy, even a slight directional preference in their emission delivers a significant kick. There's direct evidence. Some pulsars are seen far from the center of their own supernova remnants, with a trail of disturbed gas behind them, moving outward at high speed. In some cases, the direction and speed can be measured and traced back to the explosion site. So a neutron star is not only the compressed heart of a dead star, it's usually a fugitive, thrown out of its birthplace at hundreds of kilometers per second, crossing the galaxy on a path that will never return. When a neutron star has a companion and pulls material from it, the material doesn't simply land quietly. It builds up, and eventually it ignites. Hydrogen and helium accumulate on the surface, compressed by that enormous gravity into a layer of extraordinary density. And when the layer reaches a critical thickness, after hours or days, the base becomes hot and dense enough to fuse all at once. The result is a thermonuclear flash covering the entire surface, releasing in a few seconds as much energy as the sun produces in a week. It's called a Type 1 X-ray burst, and thousands have been observed from dozens of sources. The bursts repeat at intervals from hours to days, as the layer rebuilds and detonates again. Some sources have been observed doing this for decades. Occasionally, something larger happens. A superburst is a much rarer, much longer event, lasting hours rather than seconds, thought to be the ignition of a deeper layer of carbon, built up over years beneath the shallower fuel. And during a burst, the emission can reveal the star's properties, the way the brightness evolves, and how the radiation pressure of the burst itself can briefly lift the atmosphere, give constraints on mass and radius. So a neutron star in a binary system is not a quiet object. It's the site of a repeating thermonuclear event covering a surface the size of a city several times a week, in some cases continuously, for as long as anyone has been watching. Here's a small and strange topic that connects to a large search. We said the surface is extraordinarily smooth because the gravity flattens everything. Calculations put the maximum height of any feature at something like a fraction of a millimeter, perhaps a few centimeters at the very most, depending on the crust's strength. But even a bump that's small matters because of the rotation. A rotating object with any asymmetry radiates gravitational waves continuously, not a burst, like a merger, but a steady tone at twice the rotation frequency. The amplitude depends on how lopsided the star is, quantified by something called ellipticity. And for a millimeter scale mountain on a 20-kilometer sphere, the signal is fantastically weak, far below what current detectors can see from a single moment of observation. But a continuous signal can be accumulated. If you know the frequency and can track it precisely, which pulsar timing provides, you can integrate months or years of data and dig the signal out. Searches have been running for years on dozens of known pulsars. Nothing has been detected, and the upper limits are now genuinely informative. For several pulsars, the limits show that any mountain must be smaller than a few centimeters, and in the best cases, under a millimeter. Which is a remarkable thing to be able to say. We have measured, from thousands of light years away, that the surface of a particular object is smoothed to within a millimeter, not by seeing it, but by not hearing the gravitational note it would make if it weren't. There's an idea in this field that goes further than everything else, and it's worth a careful chapter. Ordinary matter is made of up and down quarks, but there's a third, heavier type, the strange quark, and there's a hypothesis, proposed in the 1970s and 80s, that matter containing roughly equal numbers of all three might actually be more stable than ordinary nuclear matter at high density. If that's true, then the cores of massive neutron stars might convert into strange quark matter, and in the most extreme version, an entire star might convert, becoming what's called a strange star, an object held together not by gravity acting on separate nucleons, but by the strong force acting on a single continuous mass of quark matter. Such an object would differ observably. It could be smaller for a given mass, could spin faster before breaking up, and would have a sharp surface rather than a crust in the usual sense. The hypothesis was taken further by some. The suggestion that a fragment of strange matter, if it existed, might convert ordinary matter it touched. That idea circulated in the 80s and produced some anxiety, and it's worth stating plainly why it isn't a concern. The conversion requires conditions that don't occur outside the cores of dense stars. Cosmic rays have been striking the Moon and the Earth with enormous energies for billions of years without incident, and the whole scenario depends on a hypothesis that is unconfirmed and considered unlikely by most of the field. So it's an interesting theoretical possibility about the interiors of the densest objects, and nothing more than that. Some observed neutron stars have been proposed as strange star candidates on the basis of unusual radii, and none of those claims has held up. Let's do something visual for a chapter, because the appearance is genuinely peculiar. A neutron star is small and, if it's old and cool, faint, but a young one is extremely hot, with a surface temperature of 1,000,000 degrees or more, which means it radiates mostly in X-rays and appears blue-white in visible light. The strange part is the shape you'd see. Because the gravity bends light so strongly, photons leaving the far side curve around towards you. The result is that you'd see substantially more than half the surface at once, depending on the compactness, perhaps 3/4 of it. Which means the star would look like a sphere with its far side wrapped around the edges. Features that should be hidden appearing near the rim, compressed into a thin band. If it had markings, you could see the back of it from the front. There's also gravitational redshift. Light climbing out of that gravitational well loses energy, so everything appears shifted toward the red by a substantial factor, around 20 to 30% for a typical neutron star. That shift has been measured in some spectra, and it directly constrains the mass-to-radius ratio. And if it's spinning fast, the surface at the equator is moving at a large fraction of light speed, which produces additional effects, the approaching side brighter and bluer, the receding side dimmer and redder. So a close-up view would show a small blue-white sphere, hotter than anything else in the sky, showing you most of its own surface at once, with one limb brightened and the other dimmed, turning hundreds of times a second. Let's do a calm thought experiment, since we did the same for black holes on another night. From a great distance, a neutron star's gravity behaves exactly like any other object of the same mass. At the distance of the Earth's orbit, a 1.4 solar mass neutron star would hold a planet in an orbit essentially identical to ours. There'd be no light and no warmth, but the orbit would be ordinary. Move closer, and the tidal forces begin to matter. The difference in gravitational pull between your head and your feet. Because the object is so compact, you can get very close to its center, and tidal forces rise as the inverse cube of distance. At a few thousand kilometers out, the stretching would become noticeable. At a few hundred, it would exceed what any material could withstand. Long before reaching the surface, anything falling in would be pulled into a stream. And there's the radiation. A young neutron star's surface is at 1,000,000 degrees, blazing in X-rays. A pulsar's beams carry enormous energy. An accreting one is surrounded by gas heated to millions of degrees. The environment is lethal, long before gravity is. So unlike a supermassive black hole, where the horizon can be crossed gently, there's no gentle approach to a neutron star. It's a small, hard, blazing object with an extreme gradient around it, which is worth saying only to make the point that this is entirely a thought experiment. The nearest one is 400 light-years away, doing nothing, drifting through the galaxy as it has for millions of years. Since we're being reassuring, let's address the question directly and then set it aside. Neutron stars are moving fast, hundreds of kilometers per second, which sounds alarming until you consider the distances. The nearest is 400 light-years away. Even at 1,000 kilometers per second, crossing that distance would take over 100,000 years, and only if it happened to be aimed directly at us, which nothing is. The galaxy is also extraordinarily empty. The average distance between stars in our neighborhood is several light-years, and objects passing through a solar system is a rare event, even over billions of years. Our own system has been essentially undisturbed for its entire history. There's no known neutron star on any trajectory that brings it near us, and the surveys that map stellar motions, which now cover nearly 2 billion objects, have found nothing of concern. As for supernovae, a nearby one could in principle affect the Earth's atmosphere, and the usual estimate is that it would need to be within about 30 light-years to do real damage. There are no candidate stars that close. The nearest plausible supernova progenitors are hundreds of light-years away, far enough that an explosion would be a spectacular light show and nothing more. So this whole subject is, from a practical standpoint, entirely remote. It's physics happening at distances that make it purely a matter of curiosity, which is exactly what we want for the middle of the night. Let's spend a chapter on why physicists care so much, because the motivation is specific. The interior of a neutron star is the only place in the present universe where matter exists at densities above that of an atomic nucleus. Particle accelerators can briefly create hot dense matter in collisions, but the conditions are different, hot and expanding rather than cold and compressed, and lasting a fraction of a second. So neutron stars are the only laboratory for cold, ultra-dense matter, and they're the only way to find out how the strong nuclear force behaves in that regime. That matters beyond astronomy. Understanding the strong force at high density bears on the theory of quarks and gluons generally, on the phase diagram of nuclear matter, and on what happened in the first microseconds after the beginning, when the whole universe was above that density. And the measurements are now coming from several completely independent directions. Masses from pulsar timing, radii from X-ray pulse profiles, tidal deformabilities from gravitational waves, cooling curves from X-ray observations of isolated stars. Each constrains the equation of state differently, and together they're converging. 20 years ago, the theoretical possibilities spanned a wide range. Today, a large fraction of that range is excluded. So the answer to why study neutron stars is because they're the only place where a fundamental question about matter can be answered, and because for the first time we have several ways of asking. There's one more use of pulsars worth a chapter, because it produced a major result recently. We discussed how precisely millisecond pulsars keep time. Now suppose a gravitational wave passes through the space between us and a pulsar. It stretches and squeezes that space slightly, which changes the light travel time, which shifts the pulse arrival times by a tiny amount. A single pulsar can't reveal this, because you couldn't distinguish it from other timing noise. But monitor dozens of pulsars across the sky for decades and look for correlations, because a passing wave affects different directions in a specific, predictable pattern. That's a pulsar timing array, and several collaborations have been running them since the 2000s, observing regularly, accumulating data year after year. In 2023, several of them announced consistent evidence for a background of gravitational waves at extremely low frequencies, periods of years rather than the fractions of a second that ground-based detectors see. The most likely source is the combined signal of supermassive black hole pairs, orbiting each other in the centers of merged galaxies throughout the universe, millions of them, at various distances, their waves overlapping into a low hum filling all of space. Which means the technique works. A network of dead stars scattered through the galaxy, each flashing hundreds of times a second, used collectively as a detector the size of the galaxy, sensitive to space-time ripples with wavelengths measured in light years. A smaller application, and rather a charming one. Because pulsars keep time so precisely and are visible from anywhere in the galaxy, they can be used for navigation. If you know the periods and positions of several, and you measure the arrival times of their pulses, you can work out your own position in 3 dimensions. The same principle as satellite navigation, but with natural transmitters and no infrastructure required. NASA has demonstrated this in orbit, using an X-ray instrument on the International Space Station to determine its position autonomously to within a few kilometers, using pulsars alone. The idea is that a spacecraft in deep space could navigate without contact with Earth. There's an older use as well. The plaques attached to the Pioneer spacecraft in the 1970s and the covers of the Voyager records include a diagram, a starburst pattern of 14 lines radiating from a point with binary numbers along each. That's a pulsar map. Each line points toward a pulsar, and the number encodes its period. Since pulsar periods change slowly and predictably, anyone finding the spacecraft could in principle work out both where the Sun is and roughly when the object was launched. It's an address written in dead stars, on the assumption that any finder would recognize pulsars and know how to use them. Whether that's optimistic is beside the point. What I like is the reasoning. Needing to write down a location that would still be meaningful in a million years, and choosing objects whose ticking is the most reliable thing anyone could think of. Let's spend a chapter on the history, because these objects were imagined decades before anyone had reason to think they were real. The neutron itself was only discovered in 1932 by James Chadwick. Within about a year, two astronomers, Walter Baade and Fritz Zwicky, proposed that a supernova might represent the transition of an ordinary star into a star composed of extremely closely packed neutrons. That's a remarkable leap. A new particle is discovered, and within months, someone proposes that entire stars might be made of it, and correctly connects that to supernovae, and coins the term supernova in the same series of papers. Zwicky, as we've discussed on other nights, was a difficult and brilliant man who was right about a great many things nobody believed at the time, including dark matter, which he proposed the same year. Then, in 1939, Robert Oppenheimer and George Volkoff worked out the detailed structure, building on work by Richard Tolman, producing the equations that still bear their names and that determine the maximum mass. Oppenheimer also showed, with Hartland Snyder, that above that limit collapse continues indefinitely, which was the first serious description of what we now call a black hole. And then almost nothing happened for nearly 30 years. The objects were considered a theoretical curiosity, far too small and faint to ever detect, and the topic largely sat still, until a graduate student found a centimetre of scruff on a chart recording, and the whole field opened at once. Let's be honest about the gaps, because there are several, and they're substantial. We don't know what's in the deepest part of the core, whether hyperons appear, whether quark matter forms, whether there's a phase transition somewhere inside, all open. We don't know the maximum mass precisely. The range has narrowed considerably, but the exact figure would immediately settle a great deal about the interior. We don't fully understand the explosion mechanism. Simulations of core collapse have improved enormously, and three-dimensional models with detailed neutrino transport now explode reasonably often, but not always, and the sensitivity to details is uncomfortable. It's not a solved problem. We don't understand the emission mechanism of pulsars in detail. 55 years after the discovery, exactly how the radio beams are produced remains debated. The general picture is agreed, the specifics are not. We don't know what fast radio bursts are, though magnetars are now the leading suspect after one was observed emitting a burst within our own galaxy in 2020. And we don't know how neutron star kicks work in detail, or why the magnetic fields vary so enormously between objects, or what governs the transition between different observed classes. That's a lot of open questions for objects we've been studying since 1967, which is a reasonable summary of the field. The broad picture is solid, and nearly every specific mechanism is still being worked out. The instruments arriving over the next couple of decades are aimed squarely at those gaps. Gravitational wave detectors are being upgraded, and next-generation facilities are being designed. Instruments with arms tens of kilometers long, buried underground to reduce noise, that would detect neutron star mergers throughout most of the observable universe rather than the nearby fraction. Instead of a handful of events, there would be thousands per year, and each one carries information about the equation of state. Large radio arrays under construction will find far more pulsars. Estimates suggest the known population could increase by an order of magnitude, including many more millisecond pulsars for timing arrays, and, if we're lucky, a pulsar orbiting a black hole, which would be an extraordinary laboratory for testing gravity. X-ray missions in development will measure more radii more precisely, and will study the surfaces and atmospheres in more detail. And there's the possibility everyone quietly hopes for: a supernova in our own galaxy. It's overdue by the usual statistics, perhaps 1 or 2 per century, and the last clearly observed one was in 1604. When it happens, the neutrino detectors that now exist would record not 24 events, but tens of thousands, mapping the collapse second by second, and gravitational wave detectors might record the asymmetry directly. That single event would settle several of the open questions at once. It could happen tonight or in 200 years, and there's no way to know which. Let's take stock, gently, before we start winding down. We know neutron stars exist, and we know a great deal about them. Thousands are catalogued. Their masses are measured precisely. They're radiated increasingly so. We've watched two collide and seen the heavy elements form. We've used them to test general relativity to a fraction of a percent, and to detect gravitational waves twice over, by two entirely different methods. We know they're the collapsed cores of massive stars, held up by neutron degeneracy pressure and the repulsive part of the strong force, at densities comparable to an atomic nucleus, in spheres about 20 kilometers across, containing more mass than the Sun. We know the surface is crystalline and extraordinarily strong, that the crust contains structures named after pasta, that the interior is probably a superfluid, and that glitches in rotation give us evidence for it. And we do not know what's at the very center, whether it's more of the same or something with new particles, or a phase of matter that hasn't existed since the first microseconds of the universe. So the honest answer to tonight's question, what is a neutron star and why is it so dense, is it's what's left when gravity removes the empty space from matter. And it's dense because atoms are mostly nothing, and gravity is patient. And the deepest part of the answer, about what that compressed material actually becomes, is still being worked out by people using dead stars as a laboratory, because no other laboratory will do. It's worth a chapter on the other kind of stellar remnant, because the comparison makes the density easier to feel. A white dwarf is what a star like our Sun leaves behind. No collapse, no explosion. The outer layers drift away over thousands of years, and the exposed core remains, about half a solar mass in a sphere roughly the size of the Earth. That's already extraordinary. A teaspoon of white dwarf material weighs a few tons. The gravity at the surface is around 100,000 times ours. It's held up by electron degeneracy pressure, that quantum counting rule we met early on, with the electrons pushed close, but not close enough to merge with the protons. There are billions of them in our galaxy, and several are visible in small telescopes. The companion of Sirius, the brightest star in our sky, is one, discovered because Sirius wobbles, then identified as a faint hot point beside it, and for years nobody could believe an object that faint could be that hot and that heavy. So the sequence goes: ordinary matter, mostly empty. White dwarf, with the atoms crushed but the electrons still separate, a teaspoon weighing a few tons. Neutron star, with the electrons pressed into the protons, a teaspoon weighing hundreds of millions of tons. And then, nothing that can hold at all. Each step removes a layer of the emptiness, and each step requires a threshold of mass to force it. Our Sun will take the first step and stop there. Since the Chandrasekhar limit determines which stars become which, let's tell that story properly, because it has an unfortunate ending and a satisfying one. In 1930, Subramanian Chandrasekhar was 19, traveling by ship from India to Cambridge to begin his doctorate. During the voyage, he worked out what happens to a white dwarf as you increase its mass. He found that, as the electrons are squeezed, they move faster, approaching the speed of light. And once relativity is taken into account, their ability to provide pressure changes. Above about 1.4 solar masses, they cannot hold at all. There is no stable configuration. He presented the result in London in 1935. Arthur Eddington, the most eminent astrophysicist in the world at the time, and previously a supporter of the young man, stood up immediately afterwards and dismissed the work publicly, saying there ought to be a law of nature to prevent a star behaving in such an absurd way. Eddington's objection carried enormous weight, and the result was largely set aside for years. Chandrasekhar, by his own account, was devastated, and eventually left the subject and moved to the United States, where he worked on other areas of astrophysics for the rest of a long and distinguished career. He was right. Eddington was wrong. The limit is real, it's fundamental, and it determines whether a dying star becomes a white dwarf or something denser. Chandrasekhar received the Nobel Prize in 1983, 53 years after the calculation, at the age of 72. There's a NASA X-ray observatory named after him now, which has been watching neutron stars since 1999. Since we keep saying masses are precisely measured, let's explain how, because the technique is beautiful. If a pulsar orbits a companion, its pulses arrive earlier and later as it moves toward and away from us, which gives the orbit. But that alone doesn't separate the masses cleanly. You get a combination, and the geometry is ambiguous. The solution uses general relativity. In a suitable system, several small relativistic effects can each be measured, and each gives a different combination of the two masses. Measure 2, and you can solve for both. Measure 3 or more, and the system is overdetermined, which lets you test the theory itself. One of the most useful is the Shapiro delay. When the pulsar passes behind its companion from our viewpoint, the pulses must travel through the companion's gravitational field, where space-time is curved, and they arrive slightly late, tens of microseconds typically. The size of that delay depends on the companion's mass. So by watching for a tiny recurring lateness in a signal that is otherwise regular to a fraction of a microsecond, you can weigh a star you cannot see. That's how the heaviest neutron stars have been measured, the ones around 2 solar masses that ruled out the softest equations of state. A delay of a few tens of microseconds in a pulse arriving from thousands of light years away, measured over years, constraining the behavior of matter at nuclear density. There's a limit to rotation, and it's a nice piece of reasoning. A spinning object flies apart when the material at its equator is moving fast enough that gravity can no longer hold it. For an ordinary star, that happens at fairly modest rates. For a neutron star, gravity is so overwhelming that the limit is extraordinarily high. Calculations put the breakup rotation somewhere around 1500 to 2000 rotations per second, depending on the equation of state, so the limit itself is another probe of the interior. The fastest observed is about 716 per second, which is comfortably below. And that raises a question. If accretion spins them up, why does nothing spin faster? Recycling should be able to push them closer to the limit. One proposed answer is gravitational waves. As a star spins faster, any slight asymmetry radiates gravitational waves more strongly, carrying away angular momentum. So there may be an equilibrium where the spin-up from accretion balances the loss from radiation. If that's right, the fastest millisecond pulsars should be emitting continuous gravitational waves at a detectable level, which is one of the motivations for those searches we discussed. Another possibility is simply that the spin-up stops when the companion runs out of material to donate before the limit is approached. It's unresolved, but it's a good example of how a single observed number, the fastest rotation seen, becomes evidence about physics that can't be measured directly. Some binary systems have an ending worth a chapter, and the names the field has given them are unusually vivid. A recycled millisecond pulsar, spun up by material from its companion, becomes extremely energetic, pouring out a wind of high-energy particles and radiation, and that wind blows back on the companion. In some systems, it's enough to erode the companion away. The pulsar's radiation heats and ablates the surface of the star that fed it, driving material off into space, so that the donor slowly evaporates. Those systems are called black widow pulsars, after the spider, and the companion masses in them are tiny, sometimes only a few times the mass of Jupiter, all that remains of a star that has been steadily boiled off. There's a related class where the companion is somewhat heavier and the destruction slower, and someone decided those should be called redbacks after an Australian relative of the same spider. Some of these systems show eclipses in the radio signal. As the pulsar passes behind the cloud of material blown off its companion, the pulses dim or vanish, then return. So you can watch the evaporation happening, orbit by orbit. There's something almost narrative in it. A star gives its material to a dead companion, and the dead companion, revived and spinning hundreds of times a second on that gift, proceeds to destroy the star that gave it. Here's a small thing that I think is lovely, and it's genuinely restful. Because pulsar signals are periodic at frequencies from about once per second up to hundreds per second, they fall in or near the range of human hearing. So if you take the raw radio signal and feed it to a speaker, you can listen to it. Slow pulsars sound like a heartbeat, a steady, soft thump, once or twice a second, unwavering. The Vela pulsar, about 1,000 light years away, ticks about 11 times a second, which sounds like a low motor. The Crab pulsar, at 30 times a second, sits at the bottom of the audible range as a deep hum, and the millisecond pulsars, at hundreds of rotations per second, produce a clear tone, a musical pitch, steady and pure, generated by a 20-kilometer sphere turning in the dark. Observatories have published these recordings for decades, and they're freely available. Astronomers who work on pulsars often have favorites. What strikes me is that these are not sonifications in the artistic sense, not data mapped onto notes for effect. The signal really is a periodic wave at that frequency. Putting it through a speaker is the most direct translation there is. So there are objects out there producing steady tones that have been playing, unchanged, apart from an imperceptible slowing, since long before anyone existed to hear them. And a few of them are in the range of a human ear, and we've recorded them. There's a phenomenon discovered in 2007 that has become one of astronomy's liveliest puzzles, and neutron stars are now the leading suspects. Fast radio bursts are exactly what the name says. Flashes of radio waves lasting a few thousandths of a second, arriving from enormous distances, releasing in that instant as much energy as the sun does in days. The first was found in archival data by a graduate student examining old recordings. For years only a handful were known, and their origin was completely mysterious, with proposals ranging from colliding neutron stars to evaporating black holes to considerably stranger ideas. Then better instruments came online, and it turned out they're common, thousands per day across the sky. Some repeat irregularly from the same location. Most have been seen only once. And in April 2020, a burst was detected from within our own galaxy, from a known magnetar, about 30,000 light years away, seen simultaneously in radio and X-rays. That was decisive for at least one class. Magnetars can produce these. Whether all fast radio bursts come from magnetars is still open, and the repeaters and non-repeaters may be different populations entirely. The mechanism, how a magnetar produces such an intense, brief, coherent radio flash, is not settled. They've also turned out to be useful, because the bursts' different frequencies arrive at slightly different times, delayed by the material they pass through. Each one measures the amount of matter along its path, which has been used to locate missing ordinary matter in the space between galaxies. Here's a nice connection. Some of the best constraints on neutron star interiors come from experiments in a laboratory in Virginia. The idea is that in a heavy nucleus like lead, which has more neutrons than protons, the extra neutrons tend to sit toward the outside, forming what's called a neutron skin, a thin layer at the surface slightly richer in neutrons. How thick that skin is depends on how neutron-rich matter behaves, specifically on how the energy changes as you increase the neutron fraction. And that same quantity determines how easily a neutron star can be compressed, and therefore its radius. So measuring the neutron skin of a lead nucleus tells you something about objects thousands of light years away. The experiments use electron beams scattering off lead targets, with the measurement relying on a subtle asymmetry that requires enormous statistical precision, years of beam time for a single result. The most recent measurements gave a thicker skin than many models expected, which implies stiffer neutron matter, and therefore larger neutron star radii, sitting in mild tension with some of the astronomical measurements. That tension is exactly the sort of thing physicists enjoy. Two completely independent approaches, one using a particle accelerator and one using X-ray telescopes, disagreeing slightly about the same underlying physics. Either one has a subtle systematic error, or the theory connecting them needs adjusting. And it's a reminder that this subject isn't only astronomy. The interior of a neutron star is a nuclear physics problem, and some of the evidence comes from a target the size of a coin. Let's spend a chapter on the computational side, because modeling a core collapse is one of the most demanding calculations attempted in science. You need to follow hydrodynamics in 3 dimensions, at extreme densities, with general relativity rather than Newtonian gravity, coupled to the transport of neutrinos of several types across enormously varying opacities, with a nuclear equation of state and magnetic fields and turbulence, all at once, with the crucial physics happening in the innermost 100 kilometers over a fraction of a second. For decades, simulations were forced to simplify, one dimension, assuming spherical symmetry. And those simulations reliably failed to explode. The shock stalled, exactly as we described, and nothing revived it. Adding a second dimension helped, because it allowed convection and turbulence behind the shock, which increases the time material spends in the heating region. Some models then exploded. 3-dimensional models with detailed neutrino transport became feasible only in the last decade or so, on some of the largest supercomputers in existence, with single runs consuming millions of processor hours. And they explode, often but not always, and with a sensitivity to the progenitor star structure and to numerical details that nobody is entirely comfortable with. So the mechanism that makes neutron stars is understood in outline and not in detail, 60 years after the outline was proposed. It's not for lack of effort. It's that the problem couples half of physics together in a region 100 kilometers across for a few tenths of a second. A chapter on how this field became observational because it required leaving the atmosphere. X-rays don't reach the ground. Our atmosphere absorbs them, which is fortunate for us and inconvenient for astronomy. So until rockets could carry instruments above it, the X-ray sky was completely unknown. In 1962, a team led by Riccardo Giacconi launched a rocket intended to look for X-rays from the moon. It flew for about 6 minutes above the atmosphere, and instead of the moon, it found something entirely unexpected. An intensely bright X-ray source in the constellation Scorpius, far brighter than anything the moon could produce. That object, Scorpius X1, turned out to be a neutron star, accreting material from a companion star, the first such system identified, though it took years to work out. It remains the brightest persistent X-ray source in the sky besides the Sun. 6 minutes of observation from a rocket opened an entire branch of astronomy. Giacconi received the Nobel Prize 40 years later. Since then, there have been dedicated X-ray observatories in orbit continuously, and they've catalogued thousands of sources. Most of the bright ones are neutron stars, or black holes accreting material, objects that are essentially invisible in ordinary light and dominate the sky in X-rays. So there's a version of the sky, entirely different from the one you'd see with your eyes, in which the brightest objects are dead stars pulling material off their companions. And it was completely unknown until 60 years ago. There's a class of system discovered relatively recently that neatly confirms the recycling picture, and it's a satisfying result. The theory says a millisecond pulsar is an old neutron star spun up by accretion from a companion. That predicts a transitional phase, a system where accretion is starting or stopping, which should behave as an X-ray source when material is flowing and as a radio pulsar when it isn't. Such systems were found, beginning around 2013. They switch, over weeks or months, between an accreting X-ray state and a rotation-powered radio pulsar state, and back again, apparently depending on how much material is flowing from the companion. Only a handful are known, and they're studied intensively, because they're the missing link made visible. You can watch a neutron star change from one category into another and back, in real time, over a human timescale. There's also an even more direct confirmation, an accreting system where the pulsations were seen in X-rays, showing that material was landing on the magnetic poles of a rapidly spinning neutron star, the spin-up process caught in the act. What I like about this is that it's a prediction from the 70s and 80s, confirmed decades later by observations nobody could have made at the time. The theory said there ought to be objects in between. The instruments improved, the objects were there. Let's finish the survey with a reassurance, because people often wonder, Our Sun is nowhere near massive enough. The threshold for producing a neutron star is around 8 to 10 solar masses at the start, and even that produces the lightest ones. Our Sun is 1 solar mass. Its ending, as we've discussed on other nights, is a red giant phase in about 5 billion years, followed by the gentle shedding of its outer layers into a glowing shell, leaving a white dwarf of about half a solar mass, roughly the size of the Earth, which will cool for many billions of years. No collapse, no explosion, no neutron star. The material simply drifts away, and what's left glows from residual heat, fading gradually toward invisibility. And that's the fate of the great majority of stars. Massive stars are rare. For every star above 8 solar masses, there are many hundreds of smaller ones. So neutron stars come from a small minority of a population, which is why the galaxy has 100 million of them, rather than 100 billion. There's no star near enough to matter either. The nearest candidate for a future supernova is hundreds of light years away, and an explosion at that distance would be a remarkable light show and nothing more. So the objects we've spent tonight on are made elsewhere, by other stars, at distances that make them purely a matter of interest. Nothing near here will ever become one. There's one more use of neutron star mergers, and it's clever enough to deserve a chapter. Measuring cosmic distances is one of the oldest difficulties in astronomy. Everything depends on a chain of methods, each calibrated against the previous one, and errors accumulate. A merger detected in gravitational waves offers something different. The waveform encodes the absolute distance directly, because the signal's amplitude depends on how far away it is, and the shape tells you the intrinsic strength, so the comparison gives distance without any calibration chain at all. That's why such events are called standard sirens, by analogy with the standard candles used in optical astronomy. And if you can also identify the host galaxy, which requires seeing the light from the event, as happened in 2017, you can measure that galaxy's recession speed from its spectrum. Distance plus recession speed gives you the expansion rate of the universe. The 2017 event produced exactly such a measurement. It was less precise than the established methods, because it was a single event with an uncertain viewing angle, but it was completely independent of them. That matters, because, as we've discussed on other nights, the established methods disagree with each other by about 10%, a discrepancy that has hardened as measurements improved. A third, independent technique could eventually settle it, and with enough merger detections, it should. Let's spend a chapter on the ones that do nothing, because they're the majority, and they're strangely peaceful to think about. Most neutron stars are old. The pulsar phase lasts perhaps 10 or 20 million years. After that, the rotation has slowed enough that the emission stops, and the object simply drifts, cooling. They have no companion to pull material from, so no X-rays from accretion. They've cooled below the temperature where their surfaces glow detectably. They emit essentially nothing. So the galaxy contains something like 100 million of these cold, dark spheres, 20 kilometers across, each with more mass than the Sun, moving at hundreds of kilometers per second, invisible. Some pass in front of distant stars occasionally, and their gravity briefly focuses the light, a microlensing event, which is one of the few ways such objects can be detected at all. A handful of candidates have been found this way. Otherwise, they're simply there, unaccounted for, drifting between the stars in enormous numbers. There may well be one within 100 light years, and we'd have no way of knowing. There's something restful in that image, oddly. 100 million objects of extraordinary extremity, the densest matter that exists, spinning superfluid interiors, crusts stronger than anything, doing absolutely nothing at all in the dark for billions of years. Most of the drama in this subject belongs to a tiny minority. The rest is silence. Since we're on the quiet ones, let's follow them forward, gently, into the deep future. A neutron star has no fuel. It cools, as we discussed, rapidly at first by neutrino emission, then slowly by radiating from the surface. After 1 million years, the surface might be a few 100,000 degrees. After 100 million, considerably less. After billions, colder still. Eventually, it becomes a cold sphere of nuclear matter, at essentially the temperature of surrounding space, as dark and inert as anything can be, still holding more mass than the Sun in 20 kilometers. And then it waits. On the timescales we discussed on another night, the long eras after the last stars burn out, these objects are among the things that remain. If protons decay, they eventually disassemble along with everything else. If they don't, they persist essentially unchanged for spans of time with dozens of zeros. Some will be ejected from galaxies as those galaxies evaporate. Some will spiral into black holes. Some may collide with each other over enormous timescales, producing brief flashes in an otherwise dark universe. But mostly, they simply persist. Cold, dense, still spinning slowly, unchanged, for longer than everything that has happened so far by an enormous factor. They're among the most durable things the universe makes, sealed, inert, requiring nothing, and outlasting the era of starlight by margins that make it a brief opening chapter. A brief chapter on how these objects appear in stories, because it's more thoughtful than usual. In 1980, the physicist Robert Forward wrote a novel imagining life on the surface of a neutron star. Creatures made not of atoms but of nuclear matter, living on a crust under gravity billions of times Earth's, with lifespans and thought processes running 1,000,000 times faster than ours, because nuclear reactions are that much quicker than chemical ones. The idea is almost certainly impossible, and Forward knew it. He was a working physicist and wrote an appendix explaining which parts were extrapolation and which were invention. But he took the physics seriously enough that the book is still cited as an example of how to build a story on real constraints. What the fiction generally gets right, when it bothers, is the extremity, the gravity, the magnetic fields, the smoothness of the surface, the impossibility of approaching. What it usually gets wrong is treating them as hazards, objects that wander into stories to threaten spacecraft. In reality, they're rare, distant, and almost never encountered, even in a galaxy full of them. And what fiction rarely captures is the specific strangeness of the interior, the superfluid, the pasta phases, the quantum vortices pinning and unpinning. The real physics is considerably odder than the dramatic version, and much harder to put in a plot, because nothing about it is dangerous or exciting in a narrative sense. It's just matter behaving in ways matter can only behave in one place. Let's lay out the whole quantitative picture once, slowly, because it's satisfying in one place, and you never have to remember any of it. Mass: 1.2 to about 2.3 solar masses, with a typical value around 1.4. Above the maximum, nothing can hold, and collapse continues to a black hole. Radius: about 11 to 13 kilometers, so a diameter of roughly 24 kilometers, a city containing more material than the Sun. Density: around 10 to the 17th kilograms per cubic meter in the outer core, several times that at the center. A teaspoon weighing hundreds of millions of tons. A sugar cube weighing about as much as a mountain range. Surface gravity: around 200 billion times Earth's. Escape velocity: roughly half the speed of light. Light leaving the surface redshifted by 20 to 30%, and bent enough that most of the far side is visible from the front. Rotation: from once every several seconds for old ones, up to 716 times per second for the fastest known, with the theoretical breakup limit somewhere above 1,000. Magnetic field: around 1 trillion times Earth's for a typical pulsar, and 1,000 times that for a magnetar. Temperature: hundreds of billions of degrees at birth, falling to hundreds of thousands within 1,000,000 years. Crust strength: about 10 billion times steel. Surface roughness: under a millimeter. Population in our galaxy: perhaps 100 million to 1 billion. Number detected: around 3,000. Nearest known: about 400 light years away, doing nothing at all. Let me return to one detail and dwell on it, because it's the strangest thing in tonight's material, and it deserves a slow chapter. Inside a neutron star, the neutrons are thought to form a superfluid, a state with no viscosity at all, where flow continues forever without resistance. But a superfluid cannot simply rotate the way an ordinary liquid does. quantum mechanics forbids it. Instead, the rotation is carried in discrete units, tiny whirlpools called vortices, each carrying exactly the same fixed amount of circulation, no more and no less. To rotate faster, a superfluid doesn't spin its whole body faster, it creates more vortices. The number of vortices sets the rotation rate, and it can only change in whole steps. In a neutron star spinning several times a second, the estimated number of vortices is around 10 to the 17th. 100 million billion tiny quantum whirlpools, arranged in a regular array through the interior, each a few tens of femtometers across, all parallel to the rotation axis. That's not a metaphor or a model convenience. It's what the physics says a rotating superfluid must contain, and the same structure is observed directly in laboratory superfluids on Earth, where the vortices can be imaged as a neat triangular lattice of dots. So somewhere below us tonight, in objects across the galaxy, there are arrays of 100 million billion quantum whirlpools, held in place by pinning to a crystalline crust, slowly building strain, until occasionally a great number let go at once and the star's rotation jumps by a millionth, which we detect as a glitch in a radio signal that has been ticking steadily for decades. A chapter on the human side, because the route from ignorance to the picture we've described is worth appreciating. In 1930, nobody knew the neutron existed. By 1934, two astronomers had proposed that entire stars might be made of them. By 1939, the structural equations existed. And then almost nothing for 30 years, because there was no way to look. Then a graduate student spent 2 years building a telescope out of wooden posts and wire across 4 acres, by hand, and then analyzed 30 meters of chart paper a day, by eye, and noticed a centimetre of anomaly she could have easily ignored. Then decades of patient accumulation. Radio observatories tracking thousands of pulsars night after night, building timing models. X-ray satellites catalogued sources for years before the patterns became clear. Nuclear physicists ran accelerator experiments for months to extract a single number about the surface of a lead nucleus. Then gravitational wave detectors, instruments that took 40 years to build, through several rounds of skepticism about whether they could ever work, requiring the measurement of length changes smaller than a proton. And in 2017, all of it converged. A signal in the detectors, an alert. 70 observatories responding within hours, and thousands of people watching 2 dead stars collide and confirming where gold comes from. None of that was a single insight. It was a great many people being careful for a long time, most of them working on one small piece, most of them not individually remembered, which is what nearly all of this actually looks like from the inside. There's a small group of neutron stars with an unusually grand nickname, and they're valuable precisely because they're boring. In the 1990s and 2000s, X-ray surveys found several nearby objects that were emitting a steady, soft X-ray glow with no radio pulses, no signs of accretion, and no companion. 7 of them were identified, and someone named them after the film. What makes them useful is that simplicity. Most neutron stars we observe are complicated, surrounded by infalling gas, or beaming energetic radiation, or embedded in a nebula. These are just warm surfaces, cooling quietly, with essentially nothing else going on. Which means their spectra are close to a clean thermal glow from the surface itself, and modeling that glow gives temperature, and combined with distance gives a radius. They're among the best targets for measuring how large a neutron star actually is. They're also close, a few hundred to a few thousand light years, and their motions can be tracked, in some cases, back to the star-forming regions where they were born a million or so years ago. And they're quiet in a way I find rather pleasant to think about. No drama at all. 7 small warm spheres in our neighborhood, cooling steadily, having done nothing noteworthy in a million years, and planning nothing further. In 2014, a system was announced that turned out to be a superb natural laboratory, and it's worth a chapter. It's a millisecond pulsar orbited by 2 white dwarfs, one in a tight orbit of about 2 days, and the 2 of them together orbiting a 3rd star every year or so. a hierarchical triple with a neutron star in it. That configuration allows a test of one of the foundations of general relativity, the strong equivalence principle, which says that all objects fall the same way in a gravitational field regardless of their composition, including their gravitational binding energy. A neutron star has enormous binding energy. A white dwarf has far less. If gravity treated them differently, even slightly, then the neutron star and its close white dwarf companion would fall toward the outer star at slightly different rates, and the inner orbit would become distorted in a specific, measurable way. The pulsar's timing precision makes that measurable, and the answer is no difference, to within about 1 part in a million, the tightest such test ever performed, far better than anything achievable in the solar system. Einstein's theory has now been checked in that regime, using 2 dead stars falling toward a third, thousands of light years away, by measuring the arrival times of radio pulses. Let's think about how much energy is stored in the rotation, because it explains what powers everything. A neutron star spinning 30 times a second, with more mass than the Sun packed into 20 kilometers, holds an enormous store of rotational energy, comparable to the total energy the Sun will radiate over hundreds of millions of years. That store is what powers a pulsar. The magnetic field acts as a brake, radiating energy away and slowing the rotation imperceptibly, and the energy extracted goes into the beams and into a wind of high-energy particles streaming outward. For the Crab pulsar, the numbers work out neatly. It's slowing by about 1/100th of a second per century, which sounds like nothing. But multiplied by that colossal rotational inertia, the power released is around 100,000 times the Sun's total output. And that's exactly what's needed to light the surrounding nebula, which had been a puzzle. The cloud is glowing far more brightly than the energy from the original explosion could sustain 900 years later. The pulsar is the power supply, converting rotation into light. So the nebula you can see through a small telescope is being lit by an object slowing down. The energy comes from nothing but the spin of a collapsed core, laid down in 1/4 of a second in 1054, and it will last for thousands of years more. Since neutron stars move fast, some of them plow through the gas between the stars, and the results are visible. If a pulsar is moving faster than the speed of sound in the surrounding medium, which at hundreds of kilometers per second it usually is, it creates a bow shock, exactly like the wave in front of a boat. The pulsar's wind of high-energy particles pushes outward. The interstellar gas pushes back as the star moves through it, and the balance forms a curved shock front ahead, with a long tail streaming behind. Some of these have been imaged. One, produced by a pulsar moving at around 1,000 kilometers per second, creates a structure in glowing hydrogen-shaped, distinctively enough that it was named the Guitar Nebula. The shape changes visibly over years as the pulsar moves into gas of varying density. Others show long trails of high-energy particles behind them, sometimes stretching for many light years, mapping the star's path through space. I find these oddly moving as images. An object 20 kilometers across, thrown out of its birthplace by an asymmetric explosion, crossing the galaxy at 1,000 kilometers per second, leaving a wake in the gas behind it that we can photograph. A small, hard thing making a visible line across a region light years wide. There's a process near pulsars that's worth a chapter, because it's genuinely exotic and it's happening continuously. Near the magnetic poles, the combination of the enormous field and rapid rotation generates electric fields of extraordinary strength, strong enough to rip charged particles off the surface and accelerate them to enormous energies along the field lines. Those particles then radiate high-energy gamma rays, and in a magnetic field that's strong, a sufficiently energetic gamma ray can convert directly into an electron and a positron, matter and antimatter, created out of a photon. Those new particles are themselves accelerated and radiate more gamma rays, which produce more pairs in a cascade. The result is that the region around a pulsar fills with a plasma of electrons and positrons, continuously replenished, far denser than anything the star could supply from its own surface. That plasma is what produces the radio emission. though the details of how are, as we mentioned, still argued over after 5 decades. And some of those positrons escape into the galaxy. There's an observed excess of high-energy positrons in cosmic rays arriving at Earth, and nearby pulsars are among the leading explanations for it, though dark matter annihilation has also been proposed, and the question isn't settled. So a spinning magnet, 20 kilometers across, is continuously manufacturing antimatter out of its own rotational energy, and some of it may be arriving here. Before the recap, a small admission, and I think it's a useful one at this hour. Nobody can really picture a neutron star, not properly. The numbers are all stateable: 20 kilometers, 1.4 solar masses, a teaspoon weighing a mountain. But the mind refuses to combine them into a single image, because nothing in ordinary experience has that combination of properties. You can picture a city-sized sphere. You can picture the sun. You cannot picture the sun inside the city-sized sphere, because every intuition you have about how much material occupies, how much space was built in a world where matter is almost entirely empty. And that's the point of tonight, really. The emptiness we take for granted isn't a fixed property of matter. It's the outcome of a balance, a quantum cost of confinement versus whatever is pushing inward. Change the pushing and the emptiness goes. So a neutron star isn't exotic material. It's ordinary material with the space taken out. The same protons and neutrons that make up your hand in the same numbers, arranged without the gaps. Which means the strangeness isn't really in the star. It's in the ordinary situation, in the fact that everything around you is almost entirely nothing, held apart by a counting rule about quantum states, and that this seems normal to us only because we've never seen the alternative. There's something restful in ending there. The extraordinary object is just matter without room, and everything in this room, including you, is mostly room. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began with your own hand, and the fact that it's almost entirely empty. Every atom is a tiny heavy nucleus, surrounded by a vast haze of electrons, with essentially nothing in between. So much nothing that if you squeezed it all out of every person alive, the entire human species would fit in a sugar cube. And that emptiness isn't structural, it's quantum. Electrons can't be pushed closer to the nucleus without paying an enormous energy cost, and no two of them can occupy the same state, which produces a pressure that exists even at absolute zero. That rule is what holds matter apart, and it's what fails, twice, in the story of dead stars. Then a massive star, burning through its fuel in stages that grow shorter and shorter. 10 million years of hydrogen, 1,000 years of carbon, a few months of oxygen, and finally a single day of silicon, building an iron core that cannot burn. And then a quarter of a second. The core collapses from the size of the Earth to 20 kilometers. Electrons merge with protons into neutrons, releasing a flood of neutrinos. The infall halts abruptly when the material reaches nuclear density and bounces, and the shock wave stalls, and is revived by absorbing about 1% of those neutrinos, which is enough to blow apart the rest of the star. 99% of the energy leaves invisibly. We saw it once, in 1987, as 24 neutrino events across 13 seconds in 3 detectors, hours before the light arrived. And what's left is a sphere 20 kilometers across with more mass than the Sun. A teaspoon weighing something like a mountain. Gravity 200 billion times Earth's. Escape velocity around half the speed of light. So light leaving it is visibly reddened, and light passing by is bent enough that you'd see most of its far side wrapped around the edges. Underneath, an atmosphere a few centimeters deep. A crystalline crust 10 billion times stronger than steel, smooth to within a millimeter, with nuclei down at its base, arranged into sheets and tubes that physicists named after pasta. A core of frictionless superfluid neutrons threaded with resistanceless proton currents, which we know about because sometimes the vortices unpin and the whole star suddenly speeds up by a millionth, and we can see that in the timing. And magnetic fields 1 trillion times Earth's, channeling particles into beams from the magnetic poles, sweeping around as the star spins, so that from here we see a pulse, once per rotation for decades, as regular as an atomic clock, found in 1967 on a chart recording by a graduate student who wouldn't dismiss a centimetre of scruff. Those clocks then gave us the first exoplanets, the first evidence for gravitational waves through a shrinking orbit, the tightest tests of general relativity anywhere, and in 2023, a detection of the low hum of supermassive black holes merging across the whole universe. And in 2017, two of them collided 130 million light-years away, and 70 observatories watched. And the glow that followed was the light of freshly made gold and platinum, several Earth masses of it, decaying as it expanded. Which is where the gold in this room came from, and the iodine in your body, forged in the collision of two dead stars, thrown across the galaxy and gathered up into a planet 4.5 billion years ago. Let me leave you with some things to rest your attention on. Not to learn, just quiet facts, true right now, while you lie still. About 400 light-years away, an isolated neutron star is drifting through space at over 100 kilometers per second, cooling slowly, with no companion and nothing falling into it. It has been doing that for perhaps 1 million years, and will continue for billions more. 6,500 light-years away, in the constellation Taurus, a sphere 20 kilometers across is turning 30 times every second, exactly as it has since Chinese astronomers wrote down a new star in the summer of 1054, and its energy is still lighting a cloud 6 light-years wide. Somewhere in that same object, and in millions like it, 100 million billion quantum vortices are sitting in a lattice in a frictionless sea, holding the rotation, slowly building strain. In orbit above you, an X-ray instrument bolted to the space station is timing the arrival of individual photons from those objects to within 100 nanoseconds, working out the sizes of cities thousands of light-years away by the shape of their light. And in observatories across several continents, radio telescopes are recording pulses from dozens of millisecond pulsars, as they have every few weeks for over 15 years, building a record precise enough to hear the hum of black holes merging throughout the universe. All of it steady, all of it running tonight, none of it needing anything from anyone. So here's where we stop. We started with your hand and the fact that it's almost entirely empty space, that solidity is a quantum rule rather than a substance, and that if the emptiness were removed from every person alive, we'd fit in a sugar cube. And then we spent 2 hours on the objects where exactly that has happened. Gravity, given a star heavy enough, removes the emptiness. What's left is a city-sized sphere holding more than the sun, with a teaspoon weighing as much as a mountain, the densest matter that exists anywhere, made by a collapse that takes 1/4 of a second and an explosion that lasts for months. None of it is near you. The closest is 400 light-years away, drifting quietly. The sun will never become one. Nothing about this touches anything here. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. And if there's any gold in the room, a ring, a chain, a thin plating on something, those atoms were made in the collision of two dead stars billions of years ago, and thrown across the galaxy and gathered into a planet, and eventually found. You're lying near something that was forged in the exact process we've been describing, and it has been sitting quietly in a drawer ever since. Nearly everything is empty. Everything holding you up is holding on its own. Sleep well.